Welcome back and welcome to section 3, concurrency in Java. So let's take a look at what we're going to learn in this section. Firstly, we're going to begin with an introduction to multithreading, why we need it and how we can achieve it. Next, the specifics of multithreading in Java, with a particular focus on the executor service. After that, we're going to take a look at some of the common problems that you might run into when you're implementing multi-threaded programming, in particular concurrency problems like race conditions, deadlocks and live locks. After that, we'll take a look at thread safety and how we can create thread safe annotations before moving on to an example, processing a large file using the executor service. Welcome to video 1, Introduction to Multithreading and Why We Need It. So firstly, let's begin with a few definitions because it's really important that we set the context here correctly in order for you to understand some of the issues that we're going to run into a little bit later in this section. So a processor core is a single logical or physical engine capable of performing standalone execution of a program. So a processor core is essentially a processor. So it can run independently of other processor cores and execute a complete sequential execution of a given program. Next, clock speed. Clock speed is the frequency at which a processor can execute instructions expressed in hertz. So hertz is the number of instructions that get executed for each given second. And you'll probably already be used to seeing processor frequencies expressed in gigahertz. So kilohertz would be thousands of instructions per second. Megahertz is millions of instructions per second. And gigahertz is billions of instructions per second. So a 3 gigahertz processor means it can essentially execute 3 billion instructions per second, which might sound like a lot, but as we'll see, a single simple line of code is actually made up of many instructions when it gets executed on a processor. The next definition is concurrency. Concurrency is when you execute multiple programs or multiple parts of a program at the same time. So that implies that we're executing parts of our program on multiple processor cores at the same time. A thread is a single sequential chain of executions. So a concurrent program will have multiple threads, and each of those threads will be executing on a different processor core. Lastly, we have multithreading, which is when we execute multiple threads at the same time, which is very similar to concurrency. So let's start with a little bit of history. Historically, applications would execute sequentially. That is, we would execute one step and then another in a linear order until a program has completed. As applications became more complicated, processors also became faster, so execution performance increased. And historically, this has been achieved through improving both the efficiency of execution on the processor through something like architecture tweaks, so increasing the size and performance of the on-chip cache and increasing the amount of memory bandwidth available, as well as decreasing the number of clock cycles required to execute a given instruction. So these are examples of architecture tweaks. But the biggest improvement to execution performance was actually through increasing the clock speed of a CPU. So we can do all sorts of tweaks in order to reduce the amount of clock cycles required to execute an instruction. But actually the best way to improve the performance of our applications and our processors was just to increase the number of instructions we could execute for each given unit of time. So if we look at this graph here on the slide, we can see that clock speed has increased incredibly quickly with time, particularly between 1995 and 2001. Often, an application improved tremendously from increasing clock speed, such that doubling the clock speed of a CPU, or central processing unit, would actually result in nearly halving the execution time, so improving performance was easy. If we had an application that took a minute on a 1 GHz processor, chances are it would take a little over 30 seconds on a 2 GHz processor and a little over 15 seconds on a 4 GHz processor. And we can see, particularly between 1990 and 2000 and 1995 and 2001, there was a tremendous increase in processor clock speeds. And just a brief note, this is based on consumer desktop processors released by Intel. So from 1990 to 2000, clock speeds grew from around 80 MHz to nearly 2 GHz. That's nearly 2000 MHz. So that's an increase of almost 1,500% in a space of just 10 years. So that's 15 times increase in clock speed in just 10 years. And we can see prior to that, back in 1973, processor speeds were less than 1 MHz. Within 40 years, they're running at over 2 gigahertz, so over 2,000 times the clock speed of original Intel 8080 CPUs. In fact, clock speeds were clock speeds were increasing so rapidly that in 2000, it was predicted by Intel that by 2011, we would have 10 gigahertz processors. So considering that clock speeds increased by a factor of 15 times between 1990 and 2000, Intel were predicting that between 2000 and 2011, we would see a further 10 times increase in clock speed, so up to 10 gigahertz on a single processor. Now, as we know, in 2018, that didn't happen, and that still hasn't happened. We ran into a bit of a problem. So if we look at the graph extended out, by 2006, clock speeds had actually tailed off to the point where they're actually starting to decrease. Now, in order to understand why this happens, we need to think a little bit about how CPUs are made. CPUs rely on silicon transistors for switching. So transistors in the CPU actually maintain binary state, a 1 or a 0. And clock speed dictates how quickly they need to switch between states. As CPUs hit around 4 GHz, silicon transistors were no longer able to maintain their 1 and 0 state without increased voltage and thus increased thermal output. So Intel discovered that without applying enormous voltages to these transistors, they were not able to maintain their state at frequencies above 4 GHz. And that's why if you look on the internet for processors that can go significantly beyond 4 GHz, you'll find that the only way that that can be achieved is by using cooling techniques like liquid nitrogen to reduce the temperature of CPUs dramatically. And the reason for that is in order to achieve those clock speeds and maintain them stably, you have to apply an enormously increased voltage to the CPU transistors in order for them to maintain their state correctly. So that's why even in 2018, you can rarely see a CPU clock speed above 3.8 GHz, certainly not something you can buy as a consumer. So think about all those applications and all the performance improvements that we've seen from increasing clock speed. What do we do beyond 2001? If we can't improve performance by increasing clock speed, what do we do? Well, this was called the Multicore Crisis. By 2003, it was obvious that silicon as a technology and silicon as a material was reaching its limits. Another solution was going to be needed in order to meet the increasing performance demands of modern applications. So in 2005, Intel released its first multi-core processor, the Intel Pentium D. And the Pentium D contains 2 separate execution cores on the same physical CPU die. So that means it could actually run 2 different sets of instructions at the same time. This is something known as multithreading. So in theory, applications should be able to run twice as fast. However, unfortunately, and you might have guessed this was coming, that's just not the case. For the previous 40 or 50 years, we've been writing applications that are designed to execute sequentially. Lots of algorithms and applications simply aren't designed to run concurrently. For example, think about trying to parallelize making a cup of coffee. It's no good if you end up pouring the water before it's been boiled. Algorithms are exactly the same and have the potential for lots of problems when we try to parallelize them, which would result in a clash of different dependencies, such as the dependency between the water being boiled and the kettle running and pouring that water. So let's take a simple example. Imagine we have a booking system that we're trying to make faster by running across multiple cores. We've got one ticket left for a concert that booking system is controlling. User A arrives and tries to book the ticket on core 1. Core 1 checks the memory and sees that there's one ticket left. It starts the reservation process. Halfway through, user B arrives and tries to book the ticket on core 2 because core 1 is busy. Core 2 checks and sees that there's also one ticket left. It starts the booking process. We now have -1 tickets left. This sort of thing happens all the time and explains why a 12-core processor won't be able to execute a program 12 times as quickly as a 1-core processor. Now, a few years ago, if you looked on eBay for a 4-core computer, people were selling 4-core 3 GHz computers as a 12 GHz computer. And unfortunately, it's simply not the case. 4 3 GHz cores are never going to be as good as one 12 GHz core. Because at some point, an application is going to need to synchronize the state between the cores, or wait until another core has finished some work, or wait for another core to finish doing something. And if we take the booking example, what we would actually have to do when we implement it is when core 1 checks to see if there's a ticket left, it needs to lock that variable in memory such that core 2 can't modify it. and that's called thread waiting. So core 2 or thread 2 ends up waiting on thread 1 to see if it's finished its work. Now, some applications are inherently more parallelizable than others, such as video encoding. Each frame can be encoded independently from another, so it's easy to achieve linear scaling. So one last consideration before we move on. How do we maintain the order of execution in a multi-threaded environment? How do we ensure different threads aren't competing for the same shared resource? And how do we make sure threads don't lock while waiting on mutually exclusive conditions? All of this is called thread safety.